Hi everyone, my name is Maryam Tahhan. I'm a principal software engineer at Red Hat. Unfortunately, my co-presenter Alessandro Sangiorgi couldn't join us today, but I will do my best to present both parts of this talk, which is titled From Cold Start to Warp Speed, Triton Kernel Caching with OCI Container Images, and I challenge anybody to say that quickly 10 times. No, 3 times, let's be fair. So today I'm going to talk a little bit about the problem we're trying to solve, our proposed solution to that problem, which is comprised of Model Cache Utils, or MCU, and GPU Kernel Manager, GKM. And then we're going to have a bit of a demo at the end. It won't be live because I haven't made any sacrifices to the demo gods today. So before we dive directly into the problem, let's talk a little bit about Triton. So Triton is a Python-like domain-specific language for writing GPU kernels. It abstracts the low-level hardware details from the programmers so that they can essentially write a Python-like GPU kernel, and then it can take that Python-like code and compile it down into highly efficient CUDA or ROCm code that runs directly on the GPU. Now, what we're particularly interested in our domain right now is that GPU kernel gets compiled down into a cache, and that lives as a cache directory on the host. Now, the problem for Triton, and by extension, VLLM or PyTorch, essentially the frameworks that are using it, is that the first time a model is loaded, all of its kernels have to be just-in-time compiled or JIT compiled, and that introduces a startup latency. Now, in the bare metal world, that might not seem like a big issue. You're going to say to me, the cache directory is on the host. I'm running stuff on the host. I'm reusing that cache directory. I don't incur the JIT latency every time. But in the Kubernetes context, it's actually a pretty big problem, because every time a pod starts, it starts totally fresh, which means that every deployment pays that JIT tax in terms of a startup latency. There are problems, however, in the bare metal world, and they're actually related to the visibility and manageability of these compiled caches. Like, you have no idea what's in the contents of one of the directory without going deep down, manually trying to find kernel names, data related to that kernel. It's pretty difficult to manage. And so for these problems, we propose a solution that is comprised of 2 things. A utility called Model Cache Utils, or MCU, and a Kubernetes operator called GPU Kernel Manager. So you can think of MCU as like the bare metal utility for managing kernels, and it's going to be like the building block that our Kubernetes operator, GKM, uses. And when you combine them, what you can get is essentially the capability to pre-cache your compiled kernel inside an OCI container image that you can then securely distribute wherever it's needed. One of our aims is only to compile caches for exactly the hardware that is in our cluster, so we don't want to maintain more images than we need to. And then from the consumption point of view, GKM and MCU allow you to extract the cache from the OCI container image to a worker node, a Kubernetes worker node, for example, so that a pod can just use it as a regular volume. It doesn't see it as anything else other than, I already have the cache directory, I don't need to JIT compile my model kernels again, and essentially hot start the model startup time. So, like, MCU, let's talk a little bit about MCU in a bit more detail, and then we can jump into GKM in a lot more detail as well. But essentially, MCU is comprised of 2 tool sets. One set of tools is called Model Cache Manager, and that's the tool that essentially automates and improves the cache management on a host. It gives you the visibility and so on into those compiled caches. And the other tool set is Model Cache Vault, and its role is to package and distribute the model kernels. We say trusted model kernels because we use signing and other things to secure them via OCI container images. So let's even dive a little bit further down into each of these in turn, starting with MCM. So MCM is really trying to solve two problems. One is cache sprawl and two is blind spots. So like I mentioned, when you are compiling Triton kernels or you're trying to load VLLM models on your host, everything gets compiled down into these caches and you have no visibility into them whatsoever, other than you know where they relatively exist at a very high level. And your only way to kind of get rid of old kernels is to pretty much blast the whole cache. You know, you don't know if there's something in there that you would like to reuse or not. You just RM minus RF everything. So really what MCM is trying to solve is, or its goal is to make caches observable, portable, and manageable. And it does so by providing 4 functionalities. Well, maybe 5 if you consider index and search, 2 separate ones. But firstly is indexing and search, so that it's essentially capable of looking at a cache directory either from Triton or VLLM. It builds up a database of metadata on all of those kernels, which you can then query by name, by architecture, by age, by number of hits, and so on. It also provides you with the capability of pruning out the caches that are that you no longer want, need, or use, based on the same filters as the search parameters that I just mentioned earlier on. It also provides you with the capability of what we call cache warming, which is essentially taking like a VLLM model, pre-generating all of the caches for it in a container, which can then be reused again for faster startup in your environments. And the last thing is it builds in some observability for you, so you can actually record the runtime cache hits and the last access times and so on, and track the actual real cache usage for each of these GPU kernels. So let's have a look at an example of each of these in turn. So this is just an example of a search for a kernel with the name add kernel. You can obviously filter here on the parameters that we see, including name, cache directory, backend, architecture, even age. We can see for this kernel here, it has 0 hits, when it was last accessed, what backend it has, the number of warps, and where it lives in terms of directory. For the prune example here, we're just pruning all kernels that are older than 5 days, but you can also do the same filtering parameters that we just saw a little bit earlier on. We're also, you might notice the minus full in that command. That means to delete everything. If you don't use minus full, I believe it'll allow you to delete like files that are the byproducts of the compilation process that you don't actually need to store long-term in your cache, like the intermediate representations and so on. This is an example of generating a kernel cache for that Facebook model. Essentially, we pre-compiled a VLLM model by bringing up an inference server in a container. Then we can capture that cache. We can wrap it in an OCI container image, or you can tarball it, or you can do something with it, and then reuse it multiple times after to save you the process of continuously having to redundantly compile things over and over again. And last thing is the ability to track. Essentially, we've implemented a runtime tracker that allow you to monitor your cache performance, and you can use it as a direct drop-in replacement for Triton's cache manager. We believe also that because it uses Triton knobs, Python knobs, then you can also configure this throughout the system and still take advantage of this without having to make a direct code change. Just to note though, the versions that it's compatible with is Torch greater than or equal to 2.8.0 and Triton greater than or equal to 3.4.0. And that kind of covers like the MCM aspect of MCU. So let's talk a little bit about MCV, or Model Cache Vault. So as I mentioned earlier on, MCV's role is to package either the Triton kernel cache or the VLLM cache, minus the KV cache, just so everybody is aware, into OCI container images. And you do this by simply pointing MCV at your cache directory, whether it's a Triton cache directory or your VLLM cache directory. It then packages that up inside a container image, which can be pushed to a container registry like Quay or Docker Hub. And you can also sign that image using cosign. So that's kind of like the push path, let's say. for MCV. On the pull side, you can always verify the image signature with cosign, at the very start of your process. Make sure that it's a kernel that you trust. Then you ask MCV to extract the cache from the container image. It pulls it down. It actually does some pre-flight checks before extracting the kernel to make sure that it's compatible with the hardware that's actually on the system. It'll abort if it's not compatible. Obviously, that's the default mode. You can override that if you don't want to do pre-flight checks. But essentially, it'll prepare that cache directory for either VLLM or Triton. It's compatible with Docker and Podman. It works in Kubernetes environments because that's, it's just another container image. That's just how things work. And we've demonstrated, or we've measured at least almost a 2x speed up in Kubernetes for some of the models that are deployed with VLLM, and I'll show you a slide about that a little bit later on. That's, in total, I would say MCU. So we just spoke about MCM and MCV. And again, that covers like the bare metal aspect, and those things are the building blocks for the next thing that we're going to talk about, which is GPU Kernel Manager, or GKM. GPU Kernel Manager is a Kubernetes operator whose role it is to manage kernel caches in a cluster. It's to simplify their deployment and management, really, in a Kubernetes cluster. And the idea, I guess the ultimate goal for us really is just to make sure that we're accelerating the model startup times. And it's just like any other Kubernetes operator. It has CRDs, it has a controller, it has a daemon set, which is a node agent, let's say, and it has a CSI driver, a container storage interface driver. And we'll walk through an example now of how things generally work. So someone or something would create a custom resource definition for a cache. In this case, we're looking at a flash attention kernel cache for ROCm, and we specify the image for that cache here. It's in Quay somewhere. As soon as that CRD gets created, the node controller kicks in. The first thing it's going to do is verify that this is a trusted image. So it verifies the image signature with cosign. And then once that's passed that check, it's going to do another thing, which is the tag here at the end of the image. That's going to be changed into the actual resolved digest. So we don't use tags from this point on in the cluster. We only use digests because they're things that we've verified and trusted on the controller side. What's happening in the background here is that this node agent, which is running on every worker node in our Kubernetes cluster, is monitoring these cache CRDs. And as soon as it passes through these two checks and it sees that there's a resolved digest here, it starts the process of pulling that image from the registry where it's stored. It will do the pre-flight check to make sure that the hardware is compatible with the cache that's in the image. And if it is, it'll extract that cache somewhere onto the node. Now, so we'll do this for all of the cache CRDs that are created across our cluster, and we'll preload, let's say, all of these caches on each worker node in our cluster. So the actual real work starts when somebody goes to deploy a pod. So let's say someone is deploying a VLLM pod. What they're going to specify at the end of their pod is a special volume. It doesn't matter what the name of that volume is right now, but what's really important here is that it's using this CSI GKM.io driver, and it'll specify the exact cache that it wants to load, so the flash attention ROCm cache. When Kubernetes goes to deploy that pod, it'll kick the GKM CSI driver, which will essentially prepare this directory that we've pre-extracted onto the host somewhere as a volume that it'll mount directly onto the pod, and the pod goes off and starts working, and it is totally unaware of this thing. It just works like normal. There's nothing special. It doesn't have any special needs inside you don't have to make any code changes. There's nothing inside the pod that you need to do to get this to work. And so as soon as it starts up, it picks up that cache. It doesn't do a just-in-time compilation. It just reuses it. And voila, you essentially bypass that JIT penalty that you're normally paying regularly. I actually do have a demo that I'm going to show you, which is a single node Kubernetes cluster. It has GKM working in it. And what we're going to do is we're going to launch 2 pods, one with a special volume like we see in this example here, which is going to essentially start up VLLM with a Llama model, and we're going to track its output till it's fully ready to serve. And then we're going to start up a regular pod with no additional volumes, which is also a VLM pod with the same Llama model, and track its logs till it's ready to start serving. And of course, we have to do this way. Sorry, guys. Okay. So on the right-hand side of the screen, because it's the mirror of what I'm looking at, is going to be the cached pod, and on the left-hand side of the screen is going to be the regular VLLM pod. But just before I do that, I'm just going to show you that you can track like the status of the caches that have been pre-extracted onto your nodes using another type of CRD that's supported in GKM, which is just the GKM cache nodes CRD. So what we can see here is this is the GKM cache node for this particular single node cluster that I'm working on. What's interesting here is the caches part. We can see that's the Llama cache that we are that I want to preload into my pod. And what's really important here is that the kernel cache has been extracted onto the host. It actually tells you what GPUs it's also compatible with on that specific host. It has some other information, but we don't need to talk about right now. But essentially, that's my node here. So the next thing I'm just going to show you is the pod specs for the cached pod and the uncached pod. So here you can see that volume, like I spoke about, model cache volume, GKM CSI driver, and there's that cache that we saw a moment ago. And if you look up here, you'll see that volume mounted to home vllm.cache/VLM. And then the regular pod doesn't have anything special in it. Sorry. Okay. So we're going to start up the 2 pods and just follow the logs. And I did speed this up so we don't have to sit through a longer time, because some of them take a very long time to start up. So we can see for the cache pod then the total startup time is 61.52 seconds. It's just pulling that data from the actual VLLM logs. That's just a summary that I've pulled from there. And then for the regular VLLM model, it's 115 seconds. And I'm just looking for the torch compile time to show you the difference, because the Triton kernel is pre-compiled for the pod on the right. And we can see the difference is like 56 seconds for the normal VLLM pod and 11.93 seconds for the pre-cached pod. So what I did was I actually ran this experiment a few times because one data point isn't enough of a data point. And so I just wanted to show you like the torch compile time for 3 different models. Without caching is the blue bars, so higher is not good, lower is better. And the green is with the pre-caching. So we can actually see a very significant improvement in the torch compile time for the pre-cached models. And then for the VLLM total startup time, it's about a 2x improvement. You almost half the startup time for the models. And that is it. Thank you very much, folks, for attending my talk. I'm happy to take any questions you might have.